All right.
And questions are welcome in between. So if you want to type in the chat or just raise your hand or just speak up, that's all would be good too. Okay, so
Perfect.
today I am really, my goal is to let you know that while you're teaching either general chemistry or inorganic chemistry, there are many opportunities for you to introduce solid state chemistry to the general curriculum just by mentioning a little bit about solids. And so if you look at some of the concepts that we teach our students, so if you're thinking of chemistry, we're really teaching them synthesis. So reactivity, we're looking at structure. Okay, how are the elements chemically bonded to each other? And then what are some of the properties? And that's really chemistry. But I would say that when we're teaching solid state chemistry, we're utilizing all of those concepts already. So for instance, when you're talking about point groups, if you just go one step further from Schoenflies to space group international notation, then you're already moving into the solid state chemistry portion of structure. If you're talking about MO diagrams, so MO theory, you can easily, not too easily, but this is one step further to move on to bands. And so really my goal for you today, hopefully, is for you to see how natural it is to tie concepts, for instance, even the octet rule, that we teach our students to introduce them to solids. And so before we do too much of that, I do want to just kind of go in and give an intro to the periodic table, which we're familiar with, but you can see here that at room temperature here, the majority of the periodic table, what we're showing our students, they're solids already. And so there's some here that are non-solids. We have some liquid that are generally at the end of this group or over here, end of the transition metal series. But really, if you heat it up, here's beyond room temperature, so 500 K. Now you have a few species that are liquid, but still the majority is solids. And so I would say in teaching Gen Chem or even in inorganic, it would be beneficial to introduce students naturally already to solid state chemistry. And so here we can go even further, 1000 K, and then up to 2500 K. And so really solids is prevalent. And so hopefully I'm going to get you to appreciate solids today and then share that with the students. Okay, so I do want to mention that that should have been on the first slide. What I've learned is really from the notes of Gordy Miller at Iowa State University as a grad student. But another book, a resource for you if you want to look at, is this book right here. I don't know if you can see. Oh, yeah. Okay. So it's solid state chemistry, Pat Woodward, among colleagues that wrote this book. And so that would be one to put together. But really, there are just a lot of resources out there. Another one, if you're interested in synthesis, would be this. Oh, great. So this book right here would be another good book. But essentially what I have here are notes from my grad school that I've kind of picked and chosen to put together for a class. And so this is kind of the outline. I'm going to first, well, I'm not going to talk about everything, but this is what I would talk about if I'm teaching the students. And so I would mention that how you as instructors are teaching the 8 minus n rule, the octet rule, can be tied into described structure and electronic structure or chemical bonding of solids as well. And then we're going to then move on to point groups and how that can be related to space groups. And then finally to how naturally MO progresses into band theory or band structure. Okay, so we're familiar with the octet rule. 8 minus n rule telling us that this is the number of bonds that a species would have because they want to have an octet, a filled octet. And this is, we told our students this for a lot of species that are non-metal or that are on the right side of the periodic table. And so I'm kind of using that to further explain this concept here. So we have, this is ground state, first of all, okay? This can't be reached, 0 to K, but it's ground state. And if we look at the ground state of silicon, so silicon here, N equals 4, and so 8 minus 4 equals 4. And so silicon, germanium, and tin will crystallize in a diamond structure. So you can see here the tetrahedron. So here's the tetrahedron. It'll be bonded to 4 other silicon or germanium or tin, whichever one that you want to look at. Okay. Now carbon in the ground state is graphite or graphene, but similarly, it is 4 bonded because there is the pi delocalization. So you have essentially each of the carbon has a double bond and then 2 single bond. And so really, when we're talking about the octet rule, we just need to mention to the students, it relates to solids as well, and just give this example saying, okay, 8 minus n rule applies to diamond, applies to graphite or graphene. Then we can also say, okay, let's move on to now n equals 5. So with n equals 5, we're going to have 3 connections or 3 bonds essentially. So now we have, look at the structure of arsenic, it's 3 bonded. So we can then move into VSEPR theory as well. Does anyone remember what this shape is called? Trigonopyramidal. So if you want to look at that, it all ties into what we have taught our students at the molecular level. But really, we're talking about solids. So these are all extended out 3-dimensionally. And so what we have here are van der Waals interactions of you so well, not strong bonding. But essentially, that is arsenic is an example of the octet rule as well. And you can do that the same for antimony, bismuth. Phosphorus has some allotropes, and their 3 bonded are a little bit constrained. There's strain in that, but that's still 3 bonded. Then you can also tie into organic chemistry in some way. So if you, let me change the color of this to red. So if you look at this, does anyone know what this is the structure of? What we just drew? So arsenic also has that chair conformation, right? And so we can really introduce or utilize previous knowledge in either organic chemistry, even Gen Chem, and into our inorganic class and just say this is related to solids as well. Okay, so that's 3 bonded. Then we can move on to the selenium, tellurium. So selenium, tellurium crystallizes helical. So solids, again, this is your ground state, okay? Crystallizes helical with n equals 6 here. We're expecting there to be 2 bonds. And so here we have 1 bond. This is selenium that's bonded to 2 other selenium in kind of a bent structure because it's helical. And so sulfur too, with this crown right here, is 2 bonded. And so the octet rule, how we utilize to teach our students about nonmetals, apply also to solids, and especially when we're looking at the ground state. And so really the chemical bonding and structure component of solids can be touched upon here. So this is really one example of just letting you know you've already been starting to teach about solid state chemistry at the general chemistry level or even in introductory inorganic. And so that's one example. Okay, I want to move on now to this other example because I know that in inorganic chemistry, we talk a lot about point groups. And so my hope is that I'm going to introduce you to the natural progression from point group to space groups. And so if you have questions, feel free to ask. It's going to move on. Okay, so here is from point groups to space groups. And so we teach our students, at least in the US, a lot of times we teach our students the Schoenflies notation. It's really early on. So we tell them there's proper rotation, which is Cn. So we can have C2, C3, C4, C5, C6 in the molecular form, okay? Molecular form, we can have C5. We tell our students identity is E, which we call C1. Then we tell our students improper rotation, which we designate as Sn. Inversion with an I, mirror plane, principal perpendicular to the principal rotational axis is sigma h. Mirror plane parallel to the principal axis is either sigma v or sigma d. And so this is what we have taught our students, or this is what I learned as an undergraduate level in learning about point groups. Now, we just naturally tell our students this one notation is the Schoenflies notation, but there's the other notation, the international notation, or the Hermann-Maugen notation. We're naturally moving them toward crystallography and giving them kind of a heads up on space groups. And so in 3-dimensional crystallography, the allowed rotations are 2-fold, 3-fold, 4-fold, and 6-fold. So instead of Cn, all we need is an n now. And so there are some differences, though, between these 2 notations, okay? So I kind of want to point that out as a head up. And so you can see it in the improper rotation, it's starting with S3, and then S4, and then S6, but there's no S1 or S2. Does anyone know what S1 is? So S1 is just going to be a C1, so S1 would be a C1, C1 would be identity, okay, followed by a sigma h. And so S1 is just going to be your mirror plane. Okay, and so you can just tell the students that when you teach them, you're not going to introduce them to S1 because S1 is a mirror plane. And so what does S2 mean? Okay, so S2, let's try and get in the Schoenflies notation what S2 means. So looking at the diagram here, you can see that S2 is a C2 followed by a sigma H perpendicular to C2. That's the definition of S2 that we teach our students when we're teaching them point groups and symmetry operations. And so here we have this circle that I'm drawing here. It says X, Y, Z, so Z is looking down this right here. And so if we have a 180 degrees rotation or a C2, then we're going to move it over here. Okay, and so now we have X bar or Y bar, or you can call it minus X minus Y, but it's still in Z, okay, not negative Z. Okay, but now we're going to have a sigma H. So a mirror plane perpendicular to that. And so what we do with this notation is that now this is no longer pointing at us, it's pointing behind or behind the paper, so in the paper. And so now we have X minus Y minus Z minus. Okay, so S2 is the same as, does anyone know? Wow, I've muted you all. So it's the same as an inversion. Okay, so you've gone from here, this is pointing out at you, to a species that's pointing away from you. And so S2 is an inversion. Okay, so that's something that we learn in the Schoenflies notation. So those of you that are teaching inorganic chemistry, you're teaching the students Schoenflies notation. But now if you move on to the international notation, you're going to notice that for improper rotation, I'm starting with 3 bar, 4 bar, 6 bar, okay? I'm not saying that there is a 2 bar, okay? And so what is the 2 bar in international notation? So in international notation, the 2 bar is going to be a twofold followed by an inversion. That's the difference, okay? So when you're moving students from Schoenflies notation to international notation, if you want to move them into solid state chemistry, this is one of the main differences, is pointing out that this 2 bar is a twofold followed by an inversion, whereas an S2 in Schoenflies notation is a twofold followed by a mirror plane. So there's that main difference. Okay, so then what happens then? Okay, so we're going to have a twofold. Okay, so let's say we're starting off here. We're going to rotate it 180 degrees onto the other side. And then we're going to do an inversion. Okay, and so this inversion now is going to move this point right here that's pointing toward you away from you onto the beginning point, That makes sense? Any questions there? Okay, so then that means that if you have a 2 bar, it is called also what happens to our original point here? It's originally pointing at you, you do a twofold, and you have an inversion, and so it is now pointing away from you, but in the same place, and so it's just a mirror plane or a reflection. So that's the main difference, okay? So when you are introducing students from Schoenflies notation for molecular species into international notations for solids, you want to point out that S2, which is the improper rotation of Schoenflies notation, is not the same as a 2 bar, which is an improper rotation in international notation. Okay, and so that's an important part. And so SN, whatever N rotation order is not the same as N bar. And so that's important. And so if you, when you teach students molecules, you might teach them icosahedron, and so that would be including a C5, for instance. But when you move on to solids that are crystalline, that obeys 3-dimensional crystallography, so if you will, there's only 32 allowed crystallographic point groups. Okay, so of all the point groups that you can teach the students, there's many you can teach the students, there's only 32 that are necessary to move the students from a point group notation to the space group notation in solids. So I'm going to try and illustrate that a little bit. Okay, so what I mean by is this. Okay, so if you look at this right here, this parallelepiped, it has a twofold rotational axis, okay, so 180 degrees. I can take that twofold and I can lift it up and move it somewhere else, and it will still have the twofold rotation. And that translational aspect is what it means to move on to the solid state of chemistry. You have this twofold, move it somewhere else. It'll always have twofold, and there's periodicity. And so when it has a fundamental twofold rotation, and we're moving on to solids and space groups, then it can either be an orthorhombic or a monoclinic space group. Okay, we'll go into that a little bit more. If it has a fundamental fourfold, so 90 degrees, then, so here's 90, so any of these 90 degrees, then it will have tetragonal symmetry, okay? So you can lift it up, move it somewhere else. That translational aspect is what makes it a solid that we're looking at, extended solid. It can have also a threefold, so 120 degrees here, or 60 degrees, so sixfold, okay? So these are all the different ways that you can arrange it. But I was saying earlier, you can't have a fivefold if you are moving on to crystalline solids. And that is because if we try and put something with a fivefold, then you're going to start introducing gaps and holes. And so if you try and move these around, you don't get that periodicity that you would see in a crystalline solid. And so people study this is a whole other field. I studied this too, and this is for quasi-crystals. But I would say in teaching undergraduates, you don't necessarily have to go into quasi-crystals. You just want to introduce them to the 32 crystallographic point groups that obey fundamental three-dimensional crystallography without moving into quasi-periodicity. So these are all periodic that we're looking at, periodic crystals instead of quasi-periodic crystals. Okay, so then let's kind of summarize this, okay? So we have all these different crystal systems, so you will, that are derived from the 32 crystallographic point groups that obey three-dimensional crystallography, and that is really a result also of the symmetry element, okay? And there's symmetry elements that we talked about. There's identity, so instead of calling it E in the Schoenflies notation, we call it 1 in international notation. Instead of CN in Schoenflies notation, we call it N in international notation. Inversion, instead of a 1, we're going to have, instead of an I, we're going to have a 1 bar, mirror planes, and then improper rotation is this N bar that we talked about. These components right here are really what I call rotational symmetry. Yes, it can involve a mirror plane as well, but it's rotational symmetry in the sense that it's in this molecular structural motif of what's called a unit cell. But if you start including things like screw rotations or glide planes, so that is when you rotate and you displace, or you reflect and you displace, then you're introducing more translational symmetry. Now, I won't talk about this too much other than just to let you know that rotational symmetry combined with translational symmetry, along with these 32 crystallographic point groups that are compatible with three-dimensional crystallography, allows there to be only 230 space groups total. So the space groups that your students will be introduced to if they're studying solid state chemistry is going to have to be one of those 230 space groups. Okay, so let's kind of break that down a little bit. Okay, so we know that there are these crystal systems, and we know there's 230 space groups, 32 crystallographic point groups, only that are derived from certain symmetry elements. And so I'm going to break that down. Okay, these are the 7 crystal systems. The first one is a triclinic. Someone might say it doesn't have any symmetry, but really it has a C1 rotational axis. So if you have a unit cell right here, so I'm drawing the unit cell right here, where you have A, B, and C, if you have basically A, B, C not equivalent to each other, and the angle between them inequivalent, then you have triclinic. You have a triclinic space crystal system. If you have something that has a fundamental twofold rotational axis, so we talked about that earlier being orthorhombic or monoclinic, then it can be, if the A, B, and C are different from each other, then it's monoclinic. If they are different from each other with a beta angle, so this beta angle is the angle between A and C, between A and C. Okay, if they're between A and C and it's not 90 degrees, then it's monoclinic. And orthorhombic just means that they're all different, but all the angles between them are 90 degrees. I think this is a lot. So what I do is I usually just provide the students these tables so that they know, okay, which crystal system are they looking at? So then there's tetragonal, there's trigonal, there's hexagonal as well. And so you can just see, okay, the lattice parameters are they equivalent to each other? If they're not equivalent, if A and B are equal to each other and C is different, then you're looking at something tetragonal. If you're looking at A, B, and C equal to each other, it potentially could be trigonal, but it can also potentially be cubic. But really, this right here, the minimum symmetry that I'm highlighting right here, is the requirement, so to speak, to classify these certain crystal systems, okay? So if you have a cubic system, yes, A, B, and C are equal to each other, the angles between them are on 90 degrees, but it needs to have a fundamental three-fold rotational axis along the body diagonal. And so these are just 7 crystal systems you can talk to about the students and say that all 236 space groups will fit one of these 7 crystal systems. And so some things to kind of keep in mind is that you can see here the trigonal can also be identified as hexagonal, or you can also see right here cubic can also be identified as trigonal, but the difference here is really along the body diagonal. If you take the cube and you either squeeze it along the body diagonal or expand it, then you get a rhombohedral, and that's in the trigonal space group. Another thing to keep in mind is that these 3 are related to each other in the sense that they have either A and B equal to A, B, and C not equal to each other, or A and B equal to each other, or A, B, and C different from each other, but they're all 90 degrees. So all of these angles between the various lattices are the same, A, B, and C. Okay, so going from point groups to space groups. Okay, so we started out with these symmetry elements that are compatible with three-dimensional crystallography. Only 32 crystallographic point groups are compatible. There are only 7 crystal systems. And from these crystal systems, we're going to derive what are called lattice types now. So let me move over that for you to see. Okay, so here we have our unit cell. Okay, so I'm just going to put these lattice points here. And so you can see here that if you were to count the number of lattices within this unit cell, it's just 1, because each of this lattice point only contributes 1/8 to within that unit cell. Okay, so each of this corner point contributes 1/8 of a lattice point, and so there's only 1 lattice point per primitive. And so the question then becomes, what about the centering? Okay, are there any other ways that the unit cell can be filled by centering and still be compatible with the crystal system? So for instance, can you have something that is a body-centered? And when we see something that is a body-centered, in the space group, we're going to automatically see I. If we see something that has face centering in all faces, then we see F in the space group. If we have something that is C centering, so if you look at here, this is the C direction, so here's C, you have C centering, you can have B centering, you can have A centering. So those are base centering. Okay. And the thing is, for instance, if you're looking at a cubic unit cell, you won't be able to have a C centering, because if you have a C centering, then you're going to destroy the three-fold rotational axes that makes it cubic. So really, there are only certain centering types, lattice types, that would obey the crystal system requirements. So those are these. Okay, so for instance, you can have monoclinic, that is C centering. You can have tetragonal, that is I centering. You can have cubic, that is body centering. I centering is body centering, or face centering, but you won't have either A, B, or C. Because by adding these extra lattices to the various faces, you're automatically destroying that three-fold rotation. You can't have a three-fold rotation and still have lattice points that are along the faces, that are not all the faces. And so these combined form what are called Bravais lattices. So that's what we're writing here, and there are 14 of them total. Okay, so we have 7 crystal systems, 32 crystallographic point groups, and based on centering, there's just 14 different types of centering. Okay, so but this is really moving on from just the point groups and the symmetry elements we talk about all the way to 3 dimensions. And so hopefully I haven't lost you yet. Feel free to ask questions if you have any, okay? All right, so I keep talking about 32 crystallographic point groups, okay? So I'm going to kind of go into them a little bit, but not too detailed. What I usually do is I provide the students with all of the 32 crystallographic point groups that are compatible with three-dimensional crystallography. And so here we're starting with triclinic. Okay, so triclinic, you can have the Schoenflies notation. Remember, you can only have either a one-fold C1 rotation or the inversion. You can have monoclinic. Remember, monoclinic is when A, B, and C are different from each other, but then beta is not 90 degrees, etc. So you can keep going down. And so this is, again, derived from the fact that you can only have C2, C1, C3, C4, and C6. Okay. And so when we move from the point groups into the space group, the directions in which we put our symmetry elements will tell us how to kind of understand the structure a little bit more. So for instance, if we're looking at this monoclinic, okay, we're going to look at monoclinic. And so if we have this M right here, that M is corresponding to either the B direction or the C direction, okay? And so B or C direction. Whereas if we're looking at this orthorhombic, let's say we're looking at 2mm. 2mm is the international notation for C2V. Okay, so 2mm C2V, same point group. But the 2 actually corresponds to a two-fold along the A axis. The M corresponds to a mirror plane perpendicular to the B axis, and the second M right here corresponds to a mirror plane perpendicular to the C axis. And so the directions that each of these, so the going from the international notation to the space groups, we're going to get the directions that they each represent, essentially. So MMM here corresponds to mirror plane perpendicular to A, perpendicular to B, and perpendicular to C, 3 different mirror planes. You might be wondering, why are these highlighted? So these holohedral right here, this is another term for saying that that is the highest symmetry within that group. So for instance, if we're looking at triclinic, if you're looking at something with only a C1 rotational axis, that is basically no symmetry. But if it has an inversion, then C1 or CI inversion here is greater symmetry than C1. You can also see it as the order. So the higher the order, you can see it as more symmetrical, whatever you'd like to identify that. And everything that is highlighted has an inversion symmetry. And so when something has an inversion symmetry, it's going to be called central symmetric. And this is important because it's going to, basically when you do X-ray diffraction, all of your symmetry and your diffraction results are symmetrical. They're called the Laue classes. And so we're not going to go into that, but I just want to highlight to let you know that these highlighted ones are the ones you may see when you're doing X-ray diffraction experiments. Okay, so let's move on then to this tetragonal one. Okay, so with the tetragonal one, so let's say we have 4 bar 2M. Okay, that means that we're going to have a 4 bar, so that is a 4-fold followed by an inversion along the C axis, because that's in the first location of the direction. Then we're going to have a 2-fold that is along the A and the B. Okay, that's because we have these brackets right here. And that's because fundamentally having the 4-fold rotation is then going to relate the A and the B directions. Okay, because the 4-fold direct rotation is along the C axis. And so the 2-fold rotation then is along A and B. And then the mirror plane is along the diagonal, essentially. Okay, so for example, we have 4 over MMM. Okay, this is the international notation, and we might know that as D4H point group. Okay, and so this first symmetry element right here corresponds to the C direction. So that means we're going to have a C4 rotational axis, and then we're going to have a mirror plane perpendicular to that C4, and so that is all in the C. So the C4 is along the Z or the C direction, followed by the mirror plane that's perpendicular to that C direction. Okay, so that's a very first indication. And so you have to know this is along the A direction. And there's a mirror plane M along the B, okay, or in the that is containing the, oh, I'm sorry, the C, that's containing the C. Sorry, the first one is C, okay? The second one is A plus B. And the third one is A plus B, A comma B, A plus B, A minus B. Okay, and then the last one is just that diagonal. And so essentially, how you look at the space group, okay, if you get a space group, the goal is for the students to understand there are these certain symmetry elements associated with the structure just by looking at the designation of the space group. Okay, so we can go even further. Here you can see trigonal, there's hexagonal, and there's cubic. And so the main one is this cubic one I kind of want to point out. Remember that the definition of this cubic is that C3 along the body diagonal, along 1, 1, 1, okay? And so if you see a point group, for instance, that's 4 bar 3M, this 3 right here corresponds to the body diagonal. So 4 bar 3M is saying that there is a 4-fold, so 4 bar 3M. So there is a 4-fold, so C4 plus a sigma H, okay? And this is all in the A, B, and C direction, okay? So this is the very first one. Okay, then there is a 3-fold C3 along the body diagonal. And then, so that's, oops, along the body diagonal. And then there's a mirror plane that is along the 1, 1. So the diagonal of it, essentially. And so this notation is telling us exactly where the symmetry elements are, as opposed to just saying, oh, you have a TD. Okay, so the TD, the students should also know, but that's for the molecular level. When you get to solids, you're saying these directions right here are then related to the unit cell. So that's why we're going to talk about next. Questions, comments? Still here? Okay. All right, so we said there are 32 crystallographic point groups, 230 space groups total. The 230 space groups is taking into account that translational symmetry, so the Bravais lattice that we talked about, and the unit cell. So we're going to take one unit cell, move it somewhere else. That is your translational symmetry. The rotational symmetry, which we also said includes improper rotation, it includes also the mirror planes, is really what we started teaching our students. This is the one that we learn in inorganic when we're learning point groups and group theory. Okay, this is the group theory component of inorganic. And so let's kind of take what we've learned so far and apply it to an example. So we have here potassium platinum chloride, okay? And just by looking at this right here, we look at the space group and we say it's P, which means it is primitive. So P means it's primitive. Remember, we can have also C, we can have A, B, we can have I for body-centered, and we can have F for face-centering. So this first designation right here is giving you the centering. Okay, so this is a primitive unit cell. Then we have 4 over M. Okay, and this 4 right here, that 4 over is designating that we have a tetragonal unit cell because it has a fundamental C4 rotational axis. So this is a C4 followed by a sigma H. Okay, and this is all going to be in the C direction. So this is in the C, then we have mirror plane, and we have mirror plane. So we talked about that earlier. So if this is the structure itself, and this is our unit cell, so this is a structure, and this is our unit cell, then we can draw it in, and you can see here that really we have lattice points, okay, so we have lattice points here at the very corners to signify that we're dealing with a primitive unit cell. And so by definition, when we're saying something is tetragonal, because it has a 4-fold rotation, A and B are going to be equal to each other. C is going to be different, but the angles, alpha, beta, gamma, so alpha is between C and B, beta is between C and A, gamma is between A and B. All of those are 90 degrees. Okay, so by definition of this, just looking at the space groups, already we should be able to derive all of that information. That is tetragonal. Being tetragonal means A and B are equal to each other. C is different. Alpha, beta, gamma are on 90 degrees. And being tetragonal means that there's a fundamental 4-fold rotational axis along the C direction, which is what we have here, the 4 bar over M. And then these other components right here, I didn't talk about it so much, but essentially these are the elements that form the asymmetric unit cell. So these are the species, the smallest species essentially, that gets using symmetry elements associated with this particular space group is going to generate the entire unit cell. And that's what we see. So hopefully that's something that you can now apply. So basically we're moving from point groups of the students to pointing out that improper rotation of the Schoenflies notation is different from improper rotation of the international notation. And then kind of getting them to appreciate and break down space groups as we move on to solids. Okay, so we've talked now about how octet rule can be used to also introduce students to appreciate more about solids. Then we talked about how we can move from the point groups to the space groups when we're talking about structure of solids. I kind of want to move on to this other component now. But essentially all of these other parts that you see here, I would say can be tied into solids as well. So going from molecular orbitals to bands, okay? So bands is just what we use as a vernacular for looking at solids. Okay, so we teach our students MO theory. Okay? So this is an example of just two atomic orbitals. So this is your AO coming together to form MOs. Okay, and so in this case, I'm using hydrogen as an example. And so we say, let's say A equals hydrogen. Okay, so we have two hydrogens coming together. We eventually have the two atomic orbitals come together to form a bonding. Okay, and that's the molecular orbital. And we also tell our students that we have bonding and we have anti-bonding. And then there is that energy difference, which we're just going to say right now, it's the difference between the highest occupied and lowest unoccupied molecular orbital. But instead of calling these now AOs, okay, so in MO theory, we call them atomic orbitals. In fact, we call them linear combination of atomic orbitals. But instead of that, when we move on to solids, we're just going to call them a state, okay? And so just like in MO theory, where we need to have conservation of atomic orbitals, when we move on to band theory, we need to say that there is conservation of states, okay? So each line is representing a state. And the reason why I'm just going to call it a state is because I don't want to call them atomic orbitals for now, okay? And we'll talk about that in a little bit. But we have here this MO for two atoms coming together. Let's say we want to include a third atom, okay? And so instead of now having A2, we're going to just make a fictitious molecule A3, okay? And so this is the MO for A3. How many lines are we then going to have? This is just sigma bonding. So we should have one additional line. So now we have 3 lines, okay? So 3 states. Okay, so when we're talking about solids, especially crystalline solids that are extended throughout space, we're not just talking about a molecular unit anymore. We're talking about not just that unit, we're talking about an Avogadro's number of atoms, okay? So expanded throughout. Just like before when we're drawing the crystal structure of the potassium platinum chloride, there's unit cells expanded throughout. And so instead of just drawing one line, we're going to draw multiple lines, okay? So we're going to say Avogadro's number of lines, okay? But in the same way, we have sigma bonding that's lower in energy. You can call it pi bonding, you can call it delta bonding, or whatever bonding you want to call it. But essentially, the bonding is lower in energy. And we have higher in energy are the anti-bonding species. And so now, instead of calling it a bunch of these lines, molecular orbitals, we're just going to say that it's a really dense state. And so we're going to talk about a density of states. Okay, so these states are dense. But then the question then becomes, well, how dense are they? Like, are they spread out like this? Are these the energy differences essentially between each of the orbitals? Or is it more closely like this? Okay, so we don't know. So I kind of want to take you through a thought process to understand this energy difference a little bit more, okay? So we're going to use hydrogen as the hallmark, okay, kind of the standard. We're going to use hydrogen as standard. We know that's around negative 13.6 eV for that hydrogen orbital, atomic orbital, for when we're making a hydrogen molecule. Let's say now instead of this hydrogen molecule, we're going to move on to something that's solid. So copper, for instance. Copper is metallic. It's solid, okay? And so let's say we have a block of copper that is 1 cubic centimeter cubed. Okay, 1 cubic centimeter. Okay, and so we know the molar volume of the piece of copper. So let's try and figure out, okay, how many states are there, okay, or atoms within this particular block of metal. And so this is where Gen Chem comes in. So this is, you can introduce this to Gen Chem students. You can say that you can move from cubic centimeter to moles, and then from moles using Avogadro's number to atoms. And then that's how many states we have. So this is a really large number, okay? Large magnitude. Okay, that's how many states we have. And our goal is to determine, okay, what are some of the magnitudes of the energy difference here? So let's just kind of take a look. This is our 13.6 eV. I'm going to overestimate this whole range, okay? This whole range, I'm going to just call it 50 eV. You can call it 100 eV if you will, okay? So this length right here, I'm going to say, okay, that's how much energy it costs, okay? That length, so much energy. I'm going to divide that over the number of states, over the number of atoms, and you can see that it's a really small number, okay? So 10 raised to negative 22, 10 raised to negative 20. When you convert that into degrees Celsius, for instance, that's 10 raised to negative 45 degrees Celsius. That's the magnitude. And just for comparison, room temperature is 0.025 eV. Okay, so this is like really small. If you have an atom that's not an atom, but let's say you have species that are at the molecular level blinking, that's the energy level that we're talking about. And so that means that the energy difference between these states, so to speak, they're so small. In fact, instead of drawing them as individual lines, we're going to combine them all into what is going to be called a band of states instead. And this is when we move on to band theory. And so really going from molecular orbital to band theory is a natural progression when you're talking about species with so many atoms in the solid state. And so a band is just by definition a set of closely spaced orbitals, okay? And so if we look at this copper again, okay, we have this argon 3d10 4s1. This is your core orbitals. Your 4s1 is really your valence electrons. And so we can fill our band here, okay? Let's fill our band with electrons that are in the 4s orbitals. And so remember, each copper atom is going to then introduce one valence electron into the band. And so really what we have is Avogadro's number of states that are essentially half filled. And so what I'm trying to do here is I'm trying to show you, this is a half filled band, but really what it looks like is this, okay? So the bottom red being filled, okay? So the bottom half of the band is all filled and the top half is empty. And so you might be thinking, okay, copper is conducting, it's metallic, it's a solid that conducts. And so with the energy that is difference between the HOMO and the LUMO being so small, this band gap right here, okay, being so small, there's really no band gap. Electrons can very easily move from the HOMO up to the LUMO. And so the band gap or the difference between the HOMO and the LUMO is so small. And that really explains conductivity of copper using band theory, which is also, of course, connected to molecular orbital theory. And so that kind of ties back to this portion right here, but it also explains some of the properties that we use when we're talking about solids. So hopefully you learned something from this. So the goal of this is to let you know that very naturally we can introduce students to solid state chemistry. When we teach them N8 minus N rule, the octet rule, we can move on to examples, for instance, of solids already so that they can just get a glimpse into, oh, this is octet rule applied to solids. When we teach them point groups, we can tell them that there is this other notation, not just the Schoenflies notation, but the international notation that can move them from point groups into space groups so that later on when they do see space groups, it won't be completely unfamiliar or alienating. And then when we talk about molecular orbital theory, we can very naturally move on to bands by just explaining that the sheer number of atoms in a solid state is going to make these molecular orbitals or these bands into, or these molecular orbitals condense into just a line or a band. And so hopefully you learned something. And if you have any questions, I'm happy to take your questions or comments.
Thanks, Joyce. That was great. It's like really good to see that natural extension. if anyone has questions, you can either ask them or you can put them in the chat and I can ask them. And while people are thinking about that, you mentioned a couple books that were kind of hard to see. If I'll get a hold of what those books are and we'll put them in the LO for this.
Sure, yeah. So actually I forgot to reference, but a lot of what I learned and a lot of the slides I'm using, they're actually from my own graduate studies with Gordy Miller at Iowa State University. We are in the process, well, I think you're part of it too, Sarah. We're putting together a textbook for inorganic chemistry, and there's going to be a chapter on solids. And so the things that you see here is actually being written up for that chapter as well. But then if you want more in-depth examples, these are written, can you see them? Yeah, this one is written, or sometimes I use it for some of the problems that I ask my students in my solid state chemistry class. But I have an entire semester for solid state chemistry, but a lot of times with teaching inorganic or general chemistry, people might not have an entire semester. So they're just for a few slides. I think this kind of natural progression is what I would encourage you to try.
Awesome. So Claude had a couple of questions. There's like the symmetry at Otterbein links like to do point groups for molecules. And I was wondering if there's anything similar for space groups. I think there is actually.
There's a listing of the space groups. I don't know if I have, oh no, not this computer, this is a different computer. There's a listing of all the 230 space groups, and the students, I've shown them to play around with it. And then there's Vesta that they can download to then, they can then draw their structures and rotate them around. That's what I have the students do. Download Vesta and go to that link, which I can provide afterward to Sarah, if you'd like.
Great. That'd be great. Thank you.
On the Symmetry at Otterbein link, if you go to like the homepage, there is like a crystallographic symmetry link there.
I see that, and I opened it up, and at least here in Chrome, it really isn't doing anything.
Okay.
So maybe I need to be in a different
follow up on
browser.
these things. Yeah, it sounds like it's kind of new, but I'll make sure that the textbooks and everything's like included as reference or as like resources on the LO that we're going to put on Viper for this.
Yeah, and I just also wanted to mention, Joyce, that I really appreciated your development of band theory, and I hope that this video can go up on YouTube very quickly, because I just want to direct my students to that portion of the program. So a little shout out to my students if they end up watching this.
We'll get it up as quickly as we can.
Yep, yep.
Any other questions or?
Oh, I just have a quick question. Joyce, when is this textbook going to be ready? I would love to use it in my classroom.
Yeah, so Sarah might know that more. I think we have a due date now of August, but I'm not really sure if that's finalized or not. It kept getting pushed back. So yeah, I don't want to promise anything at this point, especially since this is being recorded. So, but when it becomes ready, I think it'll be publicized, especially to the Ionic Viper community.
Any other questions?
Well, I just want to follow up, if you don't mind, on Vesta. So I'm just not familiar with that. In my teaching of inorganic, I really have limited it to point groups and haven't extended to space groups. And yet inside of myself, I've said, yeah, that's something I really would like to do. So the Vesta site, what is that exactly?
Yeah, here, let me get Vesta. It's for free. Here, let me get this for you. Control C, it's in the, yep. And so it's a visualization software that the students can then draw structure of. So let's see.
Very good. I've got it up now. Thank you.
Got it? Okay, so like for instance, there's a tutorial on YouTube already, but if you have, let's say for instance, here, let me pull this over. We still have a little bit of time. So here's Vesta right here. So if you have Vesta, wow, this is really large. Yeah, it's essentially you can go and create a new, yeah, this is huge. Okay, it's because this is a different screen that I'm using, but essentially you just go in and create a new structure, and then you should be able to visualize the structure right here. And the Vesta tutorial is already on YouTube. So I think you can.
Great, great, very helpful. Thank you.